course, I promised in class I was going to make a video to complete lesson 24 and lesson 25. So in lesson 24, we have a loss of Boolean algebra. I'm actually calling that part one. So I want to welcome you to this lesson. Of course, because we want to have something to do with Boolean algebra. Of course, we need to be guided by the laws. So, among the laws of Boolean algebra, we have redundancy that we also call idempotent laws. We have commutative laws, associative laws, and so on like that. So, I'm actually going to walk us through this one at a time. Our first going to start with the redundancy law. So, by multiply A by A. So, and that give me A. So it means it is redundant. Okay, we also call that idempotent. So A plus A equal to A. So that is also, so we have, when it comes to idempotent laws, we have the one for multiplication and we have the one for addition. Another, another one on the line is commutative law. So we have two different inputs, A and B. If I multiply A by B, and if that give me B multiplied by A, so that is commutative by multiplication. Okay, so we also have a commutativity law that guide addition. So if I add A to B, and it's going to be the same thing as adding B to A. And for associative, of course, that's why we have more than three, uh, you know, inputs like A, B, C. So if I first multiply B by C and I finally multiply result by A. So if it is the same thing as multiplying A by B and finally multiply by C. So we're going to call that associative law of addition, of multiplication. So we also have associative law of addition, we're still talking about three inputs and adding B to C. And if we add the result to A, so if it's going to be the same thing as adding A to B and finally add the result to C, of course, it's associative. And from there, I want to go to double negative law. Of course, two negative is actually going to return us back to the original A. That's what it's trying to say. So if I have, it's like talking about the complement of the complement, okay? It's actually going to return us back to A. We also have a complementary loss, okay? We have for both addition and multiplication, okay? So if I multiply A by its complement, of course, it give me 0, then that's a complementary law. And if I had A to its complement and that gave me 1, of course, that's a complementary law. We also have intersection law. As you can see right now, we have a union laws. And of course, I remember in this class, I talk about De Morgan's law. Okay, the complement of the products of two inputs, if it's equal to the complement of the addition, if the same thing as the sum of the complement of A and B, and of course the complement of the sum of A and B. So if it can be written as, so what I'm trying to say specifically by De Morgan's law is that the complement of the products of A and B, if it can be written as the sum of the respective complement, okay, that is going to be regarded as first De Morgan law. If I add two inputs and I take the complement of the resulting expression, if it is the same thing as the product of the respective complements. We have a distributive laws, as you can see. We have absorption law, as you can see. Okay, so we have a common identity law. We have a consensus theorem, law. So as you can see. Okay, so you need to internalize this law. Now I want to revisit the law one at a time. trying to, talk about the truth table associated with them. Okay, so well, first I want to talk about the truth table for redundancy law for multiplication and the redundancy law for addition. A multiplied by A equal to A. Of course, that is redundancy law for multiplication. A plus A equal to A. That is a redundancy law for addition. So if A, if you're using a truth table, uh, we have possibility, um, A can, we can have 0, 0, we can have 0, 1, we can have 1, 0, we can have 1, 1. So, and using the fact that if I multiply this by this, if I multiply the same thing by the same thing, it has to give me the same value. So 0 multiplied by 0 has to be 0, okay? And it's 0 multiplied. So if you take a look at that, that's exactly. So if this is a truth table for multiplication, if I want to use this approach, it's only going to apply to this one, and this one. Okay. From the truth table, that is it. Okay. This is the one that go with the multiplicative law of redundancy. And for the truth table for all, for all gates, it's actually this. Okay. And so out of that, where you have A plus A equal to A is only occur at 1 plus at this junction and this junction. So which is the redundancy aspect of that. Okay, so if that is taken now, so I'm actually moving to the next. Okay, so we can have an example. For instance, they wanted to simplify this Boolean expression A plus A plus A plus B. So the way we can figure this out, okay, using the redundancy law of addition, that guy is actually going to be A. Okay, and of course A plus A also going to be A using the redundancy law. So which is finally I'm actually going to have that, which is this guy here. Now going to the next example now. Let me see. So I want to figure this out. Okay, so if you take a look at this guy, using the addition law of redundancy, that is just going to give us BC. Don't forget, the same thing plus the same thing has to be the same. BC plus BC has to be BC. Okay, now I want to work on this one. If I want to work on this one, I need to first work on the first two. Okay, so D multiplied by D. So now we want to talk about multiplicative law of redundancy. That's going to be D. The first part is going to be D. Then we have D. So D multiplied by D now. Okay, still applying the law, I'm actually going to have D. So finally, it's going to be A plus BC plus D, which is what I have here. Okay, so if I want to go into another example of this one, if you take a look at this guy now, okay, by multiplicative law of redundancy, that's going to be B. Okay, if I fall first, or by multiplicative law of redundancy, that's going to be C. So, at the moment, if you take a look at what I got A, B, C, and C. Now, applying the redundancy law again of multiplication, that's going to be C. And that's why we have this guy here. Okay, so we're done with the multiplicative, we're done with the redundancy law, and we did that for both multiplication and for addition. So right now, I want to go into the commutative law. And of course, we're going to look at the multiplication aspect and the addition aspect. So if you remember the other time when I was talking about AND gate, of course, the truth table for that is actually this. Okay, the truth table for, for hand is that, for hand gate is that, for all gate is that. Okay, now if I have this guy now, okay, where I have AB equal to BA, okay, so the AB, you're actually going to see, if I focusing on this one, adding A and B, okay, we give the same result as adding B and A. And what is the situation? Where can we actually have that? If you look at these results here, okay, adding A to B is the same thing as adding that. Take a look at that. So I mean, sorry, multiplying rather. So 0 multiplied by 1 is 0, and 1 multiplied by 0 is 0. So that only occur here. So that was why I'm actually extracting that out. Okay. So if I multiply, you can see A multiplied by B give us B multiplied by A. Okay. So here, it's 0, it doesn't apply to 0, 0. It doesn't apply to 1, 1. So 0 times 1 is 0, 1 times. So that's what it means. Now coming to the addition, adding A to B, the same thing as adding B to A. Okay, so if you want to see what I'm talking about, it's actually this 0 plus 1 is 1, 1 plus 0, 0. So that is that. So that is what corresponds to that. Okay. Now I want to move to the associative law. Okay. I want to move to the associative. Now, associative will involve three different sets. Okay, so this is a law for multiplication, and this is a law for addition. Okay, now if you take a look at this example where I want to add, I'm adding that. Okay, so this, I can write it as this, by way of grouping, and the moment I go here, I can use redundancy law. Okay, redundancy law can actually be used within associative law. So an A plus A, so of course, is equal to A by redundancy, okay, of addition. So finally, this is giving me this. Okay, so I want to go into double negative law. No, in the double negative law, okay, a double negative returned us back to the original A. Okay, so situation A equal to 1. Of course, the complement of that is going to be 0 because don't forget, we work with binary. We work with either 0 or 1. We work with 0 and 1. So now, if you if I do the complement again, the complement of the complement, the 0 is going to go back to 1, which is what you have here. Okay, so I want to move to an example right now on this. Okay, so here, you want to simplify this, okay? And using the fact that the double complement, okay, using the fact that the double complement of A is going to be equal to A. Of course, this guy here is going to be the same thing as that. Okay, so the final answer now, okay, for this it can be written as that. Now, the next that I want to talk about is a complementary, looking into the truth table, for our multiplication and addition again. Uh, we actually want to talk about the complementary law. And of course, we know that A multiplied by complement of A is going to be 0. And where can we have that? Of course, it's actually here. Okay. If A equal to 0, the complement of A is 1. If A equal to 1, the complement of A is 0. So multiply them, we're resolving to 0. Because of that, we actually are going to call that the complementary law of multiplication. Okay. So which is what we have here. Okay. And here. If I want to talk about using this law, adding complement to the original A, that give me 1. If you take a look at on the truth gate, in the OR truth gate, okay, we are adding two different inputs and we are ending up in 1 is this situation here. Okay, so which is the complementary aspect of the OR gate. That's exactly what I mean. Okay, now I want to move right now to another example. If you take a look at this using the complementary law, of course, this guy is going to be 0. I see have my C, I see have my D. Adding this one up, I got C plus D. So that's super cool. Easy peasy. Okay, so but what about you remember under the complementary law of addition, that this is actually what we have. If I have A, okay, plus, okay, its complement, okay, it should always give me one. Okay, so this guy is a complement of this guy. Okay, so because of that, that's why we got one. Okay, now the next that I want to go into intersection law now. Okay, the next is intersection law. Okay, in the intersection law, okay, A multiplied by 1 is A multiplied by 0 is actually 0. Okay, now because we're talking about multiplication at both sides, we're only going to talk about multiplicative. We're going to talk about hand truth table. Okay, the other time, the one we've been working on, we've been having, we're considering the hand truth table and, the whole truth table because we consider both addition and multiplication, but because of the fact that the intersection law here, intersection law number one and number two is has to do with multiplication. Okay, so if I put into consideration what I have here right now, okay, if I put into that consideration, if I use something to multiply that, I think the only condition under which that can happen is when when A is one. So 1 times 1. So that's what we're going to have. So which is about situation where A equal to 0, then I'm going to end up. So if you take a look at this, 0 multiplied by 1, that is 0. So we say A multiplied by 1 end up in A. Okay. And A multiplied by 0 end up in 0. If you take a look at what I have now, okay, we're going to consider a situation where A equal to 0 and when A equal to 1. So when A equal to 0, so 0 multiplied, also I will have that 0 times 0 and 1 times 0. So take a look at that. Okay, so so that is the provisions in lecture 24. Okay, I think I put a lot of example. Of course, here you actually going to use intersection law. Okay, B times 1 and C times 1. If you go back to the intersection law, A times 1 is A. Okay, so B times 1 is B, C times 1 is C. Okay, and that was why we arrived at that. So that was why I said we're going to be using intersection law. Okay, so the union law, we also have the union laws. Okay, so A plus 1 equal to 1, A plus 0 equal to, so in the union law, we talk about addition of both. Okay, we talk about addition of both. Okay, we talk about addition of both. Okay, so now when I have something to 1 and I actually gonna have 1, obviously when A equal to 0, of course it's gonna be that. And of course, because I'm dealing with the binary, 1 plus 1 is gonna be equal to 1 when A equal to 1. So the binary in binary, okay, we're talking about binary system, not the decimal system. Okay, so and the lot 2, okay, if I have A to 0 and I got that, so that only gonna happen in a situation where you have 0 plus 0 and I have 1 plus 0. Okay, so I'm moving. Right now I think it's easy peasy. Like I said, I think I provided more example. Okay, I actually provided more example. Okay, so I have ABC plus D plus 1. And if you're going to apply the union law, okay, if you apply the union law, okay, if you take a look at the union law, when I had 1 to A is giving me 1. Okay, here, I'm actually adding, okay, if you take a look at what I have here, okay, if you take a look at what I have here, okay, A, B, C plus D plus 1, okay, I said if at least one term is 1, then the whole sum is going to be equal to 1. Okay, if at least one term is 1, the whole is going to be 1. Okay, that's exactly what I mean. Okay, if at least 1 times 1, the O is going to be 1, and that was why I have this guy to be 1. Now, in the case here, if you look at the 1 in the parentheses, if at least 1 time is 1, the whole is going to be 1. So which means the whole of this guy, actually going to be 1. So A multiplied by 1, and that's going to be A. So that's exactly what I mean by that. Okay. So now coming into this, okay, we actually want to look into De Morgan's law. Like I said, there are two versions of De Morgan's law. Now, I wanted to take a look at this guy now. So this guy, we actually want to prove that the complement of the products is equal to the sum of the respective complement. And we actually want to use a logic circuit to do that. Okay, we want to use a logic circuit to do that. Now, if you take a look at the left-hand side, okay, so if I have A here and I have a B, okay, but if you take a look at this guy, that is AND gate. AND gate means multiply A by B. So I'm actually up to this junction, I'm actually gonna have A, B, okay, A multiplied by B. And if you take a look at this is an indication of a complement, okay? Then I'm gonna put a bar on that, and that is the left-hand side. If you want to look at the right-hand side, right? Okay, so here, if I put A here, okay, and I put B here, okay, now because of this sign, okay, what I'm gonna have here is gonna be a complement, and because of this guy, what I'm actually gonna have here is B complement. And if you take a look at this shape, that is all gates. All gate will mean adding them up. Okay, so it means I'm actually adding this plus that. Okay, so I've been able to prove that now. Okay, I've been able to prove that. Now we've been able to prove the first De Morgan law. Now I want to prove the second De Morgan law. Okay, the second De Morgan law actually say the complement of A plus B equal to the product of the respective complement. Okay, so if I look at this side now, okay, so if I actually put A here, okay, and I put B here, okay, and I put B here, okay, because of this sign, okay, that is going to be A plus B, because that's an OR gate, right? That's going to be A plus B. And because of this guy, I'm actually going to put a bar on that, which is the side. But here, if I put A here and I put B here, okay, this is going to be complement of that because of this sign. And this is going to be complement of that because of this sign. And this sign means I should multiply them. Okay, so in that regard, I'm actually going to have A complement multiplied by B complement. So which is that, okay? You can see what I just did. So that's how to show the second De Morgan's law. Okay, so the next that I'm actually so we show the identical. If I also want to make use of a table, based on the one I showed you before, or we can also make use of a table. You can see that, this equal to that when you look at that, and that equal to that. But this is using a corresponding logic circuit. So which means we got several ways of proving the first and the second De Morgan's law. You can go by logic circuit, or we go by the truth table. We can have it proved out. Okay, so that's exactly what I said. So I think I put more example. Okay, take a look at this guy now. Okay, so how do we use a De Morgan's law? Okay, we know that this guy is the same thing as this guy. Okay, by De Morgan's law. Okay, and by complementary law, if you add this to that, it's actually going to be 1. Okay, and that's why this guy is going to be plus 1. And don't forget, Whenever we had 1 by union sum, whenever any of the term equal to 1, then the result is going to be 1. Okay, the result is going to be 1. So that's exactly what I mean. Okay, the result is actually going to be 1. Okay, so I'm actually going to move right now. Okay, so I want to walk us through this. Okay, in walking us through this, okay, we can apply the Morgan's law. Okay, applying the Morgan's law, okay, this particular guy is the same as the product of the complement. Okay, and don't forget, this guy using the multiplicative law of redundancy, that's going to be B, right? If I combine another B, that would be B. So what I'm going to have here is just going to be AB. Okay, here I'm going to have AB. Can you see AB? And this guy here plus D. I'm having this guy now. Okay, if I'm having this guy now, don't forget that when I'm talking about using the complement stuff, okay, the A multiplied by A and this multiplied by that, okay, that is going to be 0. That's why you have this guy here, okay, plus D, and 0 plus D is going to be D. So that's how that is done, okay? That's how that is done. So I'm actually moving now, okay? I'm actually moving now. It's like easy peasy. Okay, so we also have a distributive law, okay? That I talk about the time distributive law number 1, the distributive law number 2, okay? And of course, we have a kind of proof for that, okay? The proof for, if you want to look at the proof for the first one, you want to look at this proof, okay? Now, we can take a look at that, okay? Can take a look at that, okay? Now, if I want to prove the situation, okay, I actually have A plus B, A plus C. Okay, if I multiply this out, this is what I'm going to have. By redundancy that we talk about, okay, at the other time, the combining, we have A plus AC, and that we actually, we can group that, okay? We have this guy now, right, by grouping, okay? By grouping, we have that. Of course, we are back at here now. You can factorize A out. When you factorize A out here, okay, you're going to have 1 plus that. And of course, if any of that is 1, the whole thing is going to be 1. So I'll have A multiplied by 1. So that will be A plus BC, okay, which is this guy here. Okay, you can see now, when I start from the right-hand side, I end up in that. Okay, so which means I've already proved that. Okay, so I started from the right-hand side. I first expand this, which lead to this. Okay, expanding this. A multiplied by A is okay, AC, BA, BC. That's exactly what you see. And AA by redundancy is A. I see have that, so I can group the one with A together. I group the one with A. Okay, then which is right here. I put it in the parentheses and I factorize A out. Okay, when I factorize A out, okay, you're gonna see inside here, there's this expression in the parentheses contain 1. And whenever one of the time is 1, everything is gonna be 1. So A multiplied by 1 is A. So you can see I have that. Okay, so and if you want to prove the other one, of course, you can also use that. This is going from the right-hand side to the left-hand side. I can also go from the left-hand side to the right-hand side, okay, proving the distributive law too, okay? So if I want to go from here to here, okay, A plus BC, okay, A is the same thing as A multiplied by 1, okay? And of course, if I replace 1 with 1 plus B, because anything plus 1 is going to be 1 here. So I'm actually having that. Okay, I use A to multiply out. A times that, I'm actually having this. Okay, now if I have that again, I multiply A by 1. Okay, I have that. Okay, then I replace Y 1 by 1 plus C. I have that. Okay, so if this is what I actually have now, I should, don't forget that A dot 1 equal A and A dot A equal A. So we replace 1 inside the parentheses. Of course, we actually have indeed. Okay, All what you just need to do now is I have A to A plus AC and AB plus that. Okay. I can factorize B out. I factorize B out. Okay. So I can write this as A plus B, A plus C, which is what you have here. Okay. So that is the end of, I think I put a lot of example that you can actually figure out. Okay. Like this one, I have this one. So I multiply A by BC, ABC, A by D, AD. I can use the law of redundancy here for these two. Okay. Because this two is going to become one. By law of redundancy, it's going to be ABC. So ABC plus ABC is ABC, which is what you see here. Then AD. And lastly, the example, if I have the complement of that, I can use the Morgan's theorem where this guy is going to be replaced by this. Okay. And if that happen, I can actually use a distributive law. Okay. Using a distributive law, okay, what I'm actually going to have, A plus B and A plus C, okay, because it's the same thing as A plus BC. If you take a look at this, we're actually applying what we derived before here. Okay, A plus BC, using the fact that A plus BC equal to that. So I can actually, uh, I can actually, so when I write that, using that that's equal to that, okay, so using that this guy equal to that, so I can at the same time, okay, have a complement plus, what I actually have right now. Okay, so because of the fact that if you compare this and this, okay, this is A and A, this is BC. So using the fact that this, I can actually rewrite this as this. And when I go here, our B complement multiplied by B0. So that plus that. So that is the final. Okay, so that is the end of lesson 24. I'm gonna make lesson 25 in another video. In case you need clarification, let me know. So bye for now, everyone.